Welcome back. Today is lecture 57, and if you recall, we are talking about passives in RF circuit. In the last lecture we talked in details about the inductor, and today we will talk about something which is similar. It is called transformer. We will talk briefly about transformer, then we will also talk about capacitors, on chip capacitors. We will talk about bond wires, bonding, wire bonding, and things like in the ground plane and things like that. Okay, so we hope to conclude our discussion on RF passives in this lecture. Okay, so over to the whiteboard here. So in the last lecture we talked about inductor, and a transformer is very similar. You basically borrow most of the concepts or understanding from an inductor to a transformer also. What does a transformer do? It transforms. When you talk about transformer, we usually think of this giant big transformers on the road. That is actually a transformer for high power, high voltage, transforming the electricity from the grid to our house. These transformers we are talking about are not like those. These are actually used in microwave circuits, and these are on chip. These are fabricated, these are tiny, these are fabricated on the semiconductor wafer. Basic concepts and physics remain more or less same, but it is implemented on the semiconductor wafer. And the purpose of these transformers is to transform one voltage or one power to another. So you can use them for things like power combining, when you combine RF powers, or you can the opposite, the power splitting. You also need them for impedance transformation, which means you transform one impedance to another value, one impedance value to another impedance value, and they are in power amplifier design, in mixers, etc. You need to transform the power, and so transformers are very important. Okay. It is like an inductor in a way that you have two coupled inductor coils. In the inductor you had just one spiral, here you are going to have two spiral, and they are coupled inductively. Again, there are different kinds of inductors. There are certain where things are shorted, but in certain they are not shorted, certain designs or topologies. There are different kinds of inductors, but here we are looking at the very basic, by the way, not in much more detail. So just like in a transformer that you probably learn in your undergrad, if you are in electrical or electronics engineer, we talk about transformers. You have a primary coil and then you have a secondary coils, and then there is an inductive coupling for which you step up or step down the ratio of the power. Same thing is happening here, except that there are two spirals, and the beauty is that you can have the spiral vertically on top of each other, or you can have laterally side by side. So this is your, for instance, one spiral, it goes below the other one here, comes here, again goes below the other and comes here. The other one will go here, okay, it will be inductively coupled here, this is, and it will come here and then it will come here, sorry, this is one primary. The other one is coming here, it goes here, here, okay. So they are not, of course, metallically short, they are separated by this spiral gap, there is a gap between both of them, right. And so this is your lateral coupling of two spiral coils. This is your vertical coupling of two spiral coils. You can see them, they are vertically coupled, and there is dielectric in between them, right, there is dielectric in between them, but the basic theory will still remain the same, which is that the voltage that you are talking here is basically your, this is L1, the inductance of this coil into di by dt minus mutual inductance times the di by dt here. M is the mutual inductance of between these two coils. Similarly, V2, the voltage that you are developing in the secondary, is your minus mutual inductance times di by dt here, plus the self inductance of this coil into di d2 by dt. Okay. So the coupling between the primary and the secondary coil is defined by this K factor, and that is basically your mutual conductance divided by the square root of the product of L1 and L2. L1 and L2 are the inductances, this inductance values of the coil L1 and L2, and M is the mutual inductance. So M by square root of L1 into L2, okay, the L1 L2 you can choose, of course, because this is a spiral coil, this is a spiral coil. So this is a spiral coil. So in the previous lecture we talked about how a spiral coil is an inductor. So you know the value of inductances L1 and L2, and based on that you can find out the K factor. The K factor should ideally be 1, that means it's perfectly coupled between the primary and the secondary, but typically it can be from 0.5 to 0.9, depending on the process and design. But this is the basic funda or basic concept behind transformer. You have either a vertical coupled or a laterally coupled two spiral lines, okay, and they will transform. There are many things about transformer. I think there are even book chapters or even entire books on RF on chip transformers. Not going to talk about that, it's very short. We are looking at here this. When we say there is a leakage in a transformer, the nomenclature or the definition is such that there is an imperfect coupling between the two coil, the primary coil and the secondary coil. If the coupling is not good, we call it leakage, and the K factor will reduce. Okay. So leakage will basically prevent the signal from the one end to reaching the other end, from coupling to the other side. Okay. So you do not want the leakage to happen, and especially with increasing frequency it becomes worse. Okay. So the way to reduce leakage, for instance, is also by shrinking the gap between the turn in the windings. This gap if you reduce, okay, between the turn in the windings, these are the turns and you want to reduce the gap between the turns in the windings, that helps reduce the leakage. Okay. So this is from the top view of a laterally coupled thing. You know, the gray color here is one coil and the blue color is the other coil, primary and secondary. From the side you can see that they are overlaid side by side because the lines are going parallel to each other on the same plane in a way. Okay. This is silicon substrate they are talking about. In vertical coupling you will only see one coil because there is another running exactly below that. You can see that in the cross section here there is one top set of coil and then there is a bottom set of coil, they are separated by the dielectric. But you need to take the bottom coil also appropriately out so that you can probe them, you can connect them or hook them up to whatever you want. Okay. So please remember, by reducing the gap between the turn in the windings you are able to improve the leakage, you are able to reduce the leakage, but this is the transformer that people put on chip. And there are many other things of a transformer, we are not going to talk about that. For instance, people will also again measure S parameter of transformer and characterize transformer model, etc., etc. Okay. Then we come to capacitors, because capacitors are very common and they are very widely used. Cannot think of an RF circuit without capacitor. Okay. Capacitors are indispensable for impedance matching, for DC blocking or RF shunting. When I say RF shunting, you are creating a low resistance low AC resistance path for an RF signal to go. It will block DC, it will let RF pass, that is your RF shunting. Okay. Similar to inductor, capacitors also have a Q factor concept, but the capacitors have typically higher Q factor than inductors, which means in a given circuit in a standard frequency range of operation, the Q factor of inductor is going to be lower than the Q factor of capacitor, which means the overall Q factor of the network or of maybe the resonator of the circuit, whatever, the overall Q factor is limited by the Q factor of the inductor because that is the lower one. The Q factor of a capacitor has a simple expression. If you ignore some of the things you can ignore, like parasitic inductance, you can ignore some of the, you can say that the series resistance includes all the parasitic resistances, etc. Then Q is given by the simple formula of 1 by frequency times the series resistance times the desired capacitance. What you see here is that the Q factor deteriorates or degrades very rapidly with frequency, which means at higher frequency, a millimeter wave beyond that, your Q factor of the capacitance will become very low very quickly, and so then your capacitor Q factor will determine or limit the Q factor of the network at super high frequencies. Why? Because the inductor Q factor does not fall that fast with frequency as the Q factor of a capacitor, and the Q factor of a capacitor is defined here as the desired electrical, because the capacitor stores electrical energy. So the desired electrical energy minus the unwanted magnetic energy because of the inductive nature divided by the metal loss, the resistive loss, that is your Q factor. Okay. Now if I look at CMOS, again we are talking about a lossy substrate, and that is terrible. When you have a lossy substrate you have a high parasitic coupling, so there you have a huge quantity of parasitic substrate capacitance that comes because of the lossy silicon substrate, and that leads to a poor Q, high loss. Okay. So if I look at a simple CMOS based capacitor, you basically short the source and the drain, okay, and this is the gate, okay, and you see on both sides you have this capacitance, on both sides you have this capacitance, and the value is not, I mean the Q factor is not very good. The way you model is that this is your desired capacitance, this is your series resistance, this is your inductances because you have metal pads, and you have a highly lossy substrate that is modeled by a substrate resistance and a substrate capacitance. Okay. This CMOS based capacitors are terrible in terms of their Q factor, so they are not good for impedance matching, but they are very good for creating RF shunt. When I say RF shunt, it means they create a low resistance path for RF signals to propagate. That is because this, although they have a large amount of parasitic capacitance, the CMOS capacitors can have very high value of capacitances. They can have few hundred of femtofarads per micron square. It is very high capacitance values can be realized with CMOS based capacitors. Okay. So, please remember that. Another way of making capacitor, and this is also useful for compound semiconductor based processes, is to have MIM. MIM stands for metal insulator metal. So, you have a metal like this, below that there is a dielectric. The dielectric could be, for instance, SiO2, maybe SiAN. Okay. It has a certain thickness that the foundry or the process will decide. You can also have, as a designer, have a certain say, but the foundry will set a limit. And the dielectric constant will depend on whether you are using silicon oxide or silicon nitride or maybe aluminum oxide or whatever you want to use, depending on the foundry that will permit you. So, that dielectric constant, and there is a metal plate here and then there is a metal below. Okay, there could be a metal below, this is the metal below. Okay. So, it is like a metal, dielectric and then a metal. So, it is metal, dielectric metal. So, the epsilon naught epsilon s into area of the top metal, the active metal divided by the thickness of the dielectric gives you the capacitance values. Okay. Now, this have lower losses because you are just looking at metal SiN or SiO2 metal, and this SiN or SiO2 could be a really good dielectric for the thickness that you are considering. You may not be able to go to very high voltages, of course, but for a given thickness you will be able to get a very good dielectric quality. So, they will tend to have higher Q factor than the lossy CMOS capacitors. Okay. But the capacitance per unit area of this MIM is lower because the only capacitance here is this, whereas in a CMOS you are talking about a depletion capacitance here. There is an oxide capacitance there. So, you are generally talking about a larger capacitance per unit area, but here you are just talking about this value epsilon s by d basically, and so the overall capacitance per unit area is lower. So, you need to have very, very large real estate to realize a reasonable amount of absolute farads or microfarads or nanofarads of capacitance, as opposed to a CMOS based process where CMOS based capacitor where you can do away with a more lower reduced footprint. Okay. This is the model that is again being talked about. Next thing we look at is varactor, and if you recall in one of our earlier lectures of this course, maybe lecture 10 or 12, we talked about varactors. Varactors basically are variable capacitors or tunable capacitors, and they are very useful, as we also talked about in lecture I guess 10 to 14 or something like that. We talked about tunable capacitors or varactors in things like phase shifters, VCOs, filters, etc. We talked about that. This can tune the capacitance over a certain voltage range. For instance, over a voltage range of 0 to some and this is negative by the way. So, 0 to minus 3 volt or 0 to minus 2 volt or something, your capacitance can change. Your Q factor also can change based on that. Your capacitance can be tuned. When you tune the capacitance, you are able to use that device in certain specific application because you are able to tune the capacitance. Whenever you tune the capacitance, okay, you are able to tune the delay also. RC delays also will change, correct, and you can create harmonics. Okay, if you recall our long back discussion. Okay, so varactors are very important. And the tuning ratio is typically defined as the maximum capacitance that you get, which is maybe this, divided by the minimum capacitance, which may be this. So, that ratio is tuning ratio, and typically this tuning ratio is less than 3, not so much in a MOS or MS structure. Okay. So, again you short the source and drain and you basically use the gate as the second port. If you use a bi-CMOS process, remember bi-CMOS process from last week I guess, you can get a tuning ratio up to 5. It is a larger and a more impressive value because you have a PN diode there. You can have a PN diode in a bi-CMOS process, and that PN diode will enable you to go a larger range of depletion, larger range of capacitance, etc., etc. If you do a hyper abrupt doping profile, this is something also we discussed in lecture 10 to 12 or 10 to 14 I guess. Hyper abrupt doping profile is that you engineer the doping profile in a very interesting manner such that you can get up to 10, a tuning ratio of 10, but this is a costly process. You need to tune the doping and foundries may not allow that. So, this is something very niche, very expensive, but you can get to that. Okay. The varactor has a Q factor very similar to capacitor, which is 1 by omega RC. So, with higher frequencies the Q factor of varactor will also degrade very rapidly. Okay. So, for instance, at 90 nanometer CMOS, and 90 nanometer SOI process. The tuning ratio in CMOS is 1.5 to 2, but in SOI it's 2 to 2.5, slightly better. The range over which you tune is around 1 volt, and the Q factor is get 10 to 16, 12 to 20, slightly better in RF SOI. This is the Q factor at 5 gigahertz. Okay, always remember that. Okay. However, in a gallium arsenide MESFET, you are going to get a Q factor which can go as high as 30 at 5 gigahertz, which is more impressive, and the range of voltage is also 3 volt. You can get up to 3. A silicon PN diode, you can get much better tuning ratio, okay, and you can operate up to 6 volt, and you can get a Q factor of more than 30. The best is of course off chip PN diode. You buy a PN diode separately, it is not integrated on the same chip. There you can get a tuning ratio of to 10 because you can do a hyper abrupt doping profile, okay, and you can get very good Q factor also because it is an off chip discrete varactor that you can buy. Okay. Now beyond the varactor, something very important is beyond the varactor, inductor, capacitors, transformers, we also have something called signal pads. We tend to ignore them, but they are very critical. You can see a signal pad here, that is a signal pad here, that is a signal pad here. Signal pads are required to connect the chip input output to the component outside the chip, the external world, for instance the antenna, or you want to bond it to a board. You need these pads to wire bond. Can you see this? These are wire bonds with gold lines. You need the pads to bond the device from the chip to the external world, maybe to an antenna, maybe to an RF PCB or a board or whatever, what have you. It is very important. You cannot directly bond a discrete device because the device is very tiny and your bond wire has a certain dimension. You cannot go lower than that. Mechanical strength, integrability, everything comes into picture. So you need to have these signal pads or bond pads which have to be wired, for instance, or which can be connected to an antenna, for instance. Okay. So the signal pads are very important, but you need to minimize the signal pad size or the area because that will directly affect your parasitic values, capacitances, for instance. You need to reduce the pad area to reduce the extra parasitic coupling to the substrate, but again you cannot probably go much lower than 50 by 50 micron of the pad size because the wire bonding will need a certain minimum pad size. If you have maybe 5 by 5 micron, you cannot do wire bonding. 10 by 10 micron, you cannot do wire bonding. So you need a typical minimum dimension, so you have to live with that, because whenever you have these pads, the pad is a part of the testing environment. You need to account for that parasitics when you are actually designing, or you have to de-embed that if you are not using a pad. Okay. So typical pads are 50 by 50 micron, and the distance from the pad to the lossy substrates could be 5 micron. Okay. Because you use different dielectrics and metals are on top of different dielectrics, remember that. So typically you try to put it on the top dielectric. So the top, you have multiple layers of dielectric. Okay. So the top to the bottom substrate could be 5 micron, you know, when I say bottom, the start of the bottom substrate. Okay. So in SOI you have lower loss, as I told you, because you have a dielectric that isolates. You can get a low loss of 0.3 dB, which is very low loss, up to 60 gigahertz in this pads, and in case of VLSI, the simple VLSI, it will be much worse. Okay. So whenever you measure transistor on an actual wafer, you need pads to enable on wafer characterization, and those pads will have massive parasitic components which need to be de-embedded. We will talk about de-embedding very soon in a lecture. Okay. We have to de-embed the effect of the pad parasitics in order to enable more accurate on wafer measurement. Okay. We will come to that. Okay. This image, this plot shows you the measured from a textbook S parameter, okay, on this side and some phase on the other side. This is the measured S parameter, this is the simulated S parameter, okay, for a signal pad. Okay. This we basically have to characterize them for S parameter anyway. S parameter tells you scattering parameter, how much you are transmitting, how much you are reflecting, all these things are, the information are conveyed by the S parameter measurement. Then we have on chip interconnect. Oftentimes you will have multiple layers of dielectric, multiple layers of metal, especially in a CMOS like process. You bring the signal up and you need these dielectrics and tungsten plugs and via holes to bring the signal up. So this is a ground pad, for instance, it's connecting to a signal pad here, but you see these are the tungsten plugs through which this is a via hole maybe, and then you are bringing this tungsten plug up. So these are called on chip interconnects because you are using these metallic lines to connect from one level to another level to another level, to routing the signal, etc. Okay. You have to remember that all these ground pads, signal pads that we talk about, typically they are not ideal at RF frequencies, and so these interconnect lines can also introduce significant parasitic components. These interconnect lines that you are using to take the metal from one level to the another level top, the routing the metal, etc., signal, routing the signal with these different metal layers, you are prone to introducing additional parasitic components with these interconnect layers also. Okay, so typically you can use a 3 metal layer for or a 4 metal layer process for on chip interconnections, inductors. You can have metal 2, metal 3, metal 4, etc. Typically metal 1 in compound semiconductor at least is not touched by the MMIC designer. It will be the first layer that comes, and beyond that when the gate layer comes they will use those layers to design their transmission lines. They will not use the first layer, the compound semiconductor I am talking about. Okay. And so this is an equivalent model. It is a pad ground, this is a pad ground, and then you have a this is the pad drain, for instance. You can model it as a parallel or a shunt combination of a resistance and a capacitance, which are introduced by these on chip interconnects. Okay. Then you have off chip lines. Off chip wiring is basically like wire bonding. I had shown an image before also, a real image. This is the image of wire bonding, you can see that. But here I am going to show you that whenever you have an IC, this is an IC, this could be a discrete die, this could be a discrete device that is diced and packaged or maybe not packaged, and then you have wires that will connect different pads, signal pads, ground pads, etc. In this case these are ground. Okay, these are the drain bias wire bonds. This is the RF input, this is the RF output. You bond it to the external circuit or the external bond board. So this external box you see could be an assembling block, they say. This could be an RF PCB or Rogers substrate or maybe a board on which you are going to assemble and make a power amplifier, a hybrid power amplifier, for instance. Okay. So these lines of course have to be matched 50 ohm, that makes it easier for circuit designer, it's a matched line, but you need wire bonds, and these wire bonds are typically made of gold. People also use copper or aluminum, but gold is the best. Okay, and they will connect these different pads of the device or the die or the IC to the PCB or the board or eval board or whatever. Okay, and typically these bond pads I told you 50 by 50 micron, typically that's the range, 30 to 100 pattern. To make a good contact between the wire bond and the pad, people use ultrasonic waves, pressure, temperature. This is an elaborate process of wire bonding, by the way. You do the wire bonding to make a good connection between the bond pads and the wire so that they don't disintegrate, they don't come off. If you do a sloppy work, if you don't do a good work, then under certain testing and all, vibration, etc., the wire may come off, and that's the end of your chip, of your board. Okay. Typical length of wires are about 0.3 millimeter to 2 millimeter. Okay, typical, I am talking typical, and they introduce in the range of 1 nanohenry per millimeter. That's the inductance that these wires will introduce. Okay, with longer wire length your inductors will increase, inductance will increase, that is very obvious. So that's why people try to minimize the bond wire length. Okay, typically when you have a substrate board like that, an RF board like that, okay, you create a notch here, a notch like you basically create like a trench or a small depth here, on which the thickness of this depth that you create, the thickness of this notch that you create is exactly the thickness of the chip or the die that you are going to put. So once you put the die over there, it fits exactly in that notch, and so it's in the same plane as the top plane. So your wire, the distance of the wire and the chip edge reduces. Otherwise what will happen is that if you don't do the notch, then your chip will have certain thickness. So the chip will sit on top like that, right? It's on the top. So when you bring the wire, it has to travel extra distance, because if I look from the side, I see a board and then I see a chip. So the top comes like that, correct? But if I create a notch, then I have a chip like that, but I create a notch like that. Okay, and so my chip sits here. So this comes here. Do you see my point? So that's how you reduce the distance between the chip edge and the bond pad. Okay. These bond wires that you use, sometimes they are a part of the design. The RF designer may use them or exploit them for his or her advantage by making them a part of the impedance matching network. Okay. These bond wires can have very high Q, by the way, because they are not limited by the substrate coupling and the lossy substrate effects and things like that. So they can have very high Q, by the way. So just remember that. Okay. Again, these are images of the bond wires. So you can see this is the inside of a package. Okay, you can see these bond wires being connecting. There's probably a discrete LDMOS or a transistor or something there. It's a die which is attached to a metal flange of the package, and you have these wires that are connecting them. Okay, these are the bond wires. This is probably the gate lead. This is probably the drain lead, or vice versa. Okay, in a LDMOS, the substrate will be the source will be the bottom flange here, of course. Okay. People use elaborate models also for bond wires. You can model the bond wire as inductor, and then there is a parallel or a shunt capacitor. Okay, that's it's an equivalent array of bond wire can be in an array of bond wire can be modeled as an equivalent circuit of this LC networks. Of course resistance also is there, but you can include that, so it is like a circuit in that. Now these two figures are very important. The top figure shows you the inductance of this array of bond wires as a function of number of wires. What do you see? You see that the inductance decreases as the total number of wires increases. Now if you have a lot of wires, you can have mutual inductance between them. You may or may not ignore, but the trend is the same. If you ignore mutual inductance, this is your plot. If you do include the mutual inductance and you assume air or some kind of dielectric in between, then the top one is the. So the values will slightly change. Okay, with no mutual inductance you get a lower inductance, that is underestimating, but the trend is the same. Okay, this decrease of inductance values with number of wires is a consequence of the coupled set of this transmission line. So it is like a, how do I say, this is like, you can say these are all parallel inductors. These are all parallel inductors, right. So if you have inductances in parallel, they will go as 1 by L1, 1 by L2, 1 by L3, etc. So with more wires, okay, these are wires with more, we can say with more wires with more inductors, it is a parallel combination of inductors. So it is like a harmonic mean, of course, it is like resistor basically, right. So you are reducing the inductance values as an increase in the number of wires. It is a coupled, it is a parallel effect. Okay. However, capacitance is the opposite. The capacitance that is induced by this inductor lines. See, these lines are ultimately they are metallic lines, they are wires of chip, okay, of chip, but they are still going to have some grounding, you know, there will be ground, and so there will be coupling, capacitive coupling to the ground, and with higher number of wires your capacitance values increases, and this is with plastic in between as a medium. You can, why are they using plastic? Because in a package you can actually do an over the mold, you know, you can fill that with plastic in a way, we will see that. So you can, and this is air, okay, but the trend is the same, which is the capacitance increases with a number of wires, because with larger number of wires you are basically increasing the coupling to the ground. You are increasing the coupling to the ground. It is a lot of capacitors in parallel, so it will add up as C1 plus C2 plus C3. You can think of it in that way. So the capacitance increases. They are all coupling to the ground. Okay. So for a very large number of wires, your capacitance will play a dominant role, because your capacitance will be very large, your inductance will be very low. Whereas for just one or two or few wires, your inductance will be large, your capacitance will be low. So just please keep that in mind. Okay. The final couple of things is here, flip chip bonding. Flip chip bonding is a very interesting concept where you basically flip the RFIC upside down. You have something called indium bumps or some kind of metallic bumps which are precisely aligned to the circuit below, where the board below where you are going to put them, and you flip it upside down and you put it. Okay. These are like soldering balls, you can say, okay, or indium bumps, people say soldering balls, and they are aligned precisely to the printed circuit board where you are going to align them, and then you use the instrument called a flip chip bonder. It will flip it and put it upside down, it will paste it, and then you get, you know, you get this. You see this is an upside down. These are the flip chip or the, you can say the indium bumps, or maybe the metal conductive solder balls. This is a transmission line on the printed circuit board. These are the transmission lines on the printed circuit board. This is precisely aligned. What is the advantage? There is no wire here, no wire bonding here. If there is no wire bonding here, then there is no extra additional inductance, right. You are able to reduce the inductance crazily, so much, right. Your inductance is super duper low because you just connect the pads directly to the printed board without having to wire bond out. Can you see the difference? Okay. And wire bonding introduces a large amount of inductances, we already discussed that. Okay. So flip chip gives you this flexibility, this compactness. It is a very compact thing, there is no hanging wires, there is no risk of wire detaching, there is no issue with large inductances coming from the wires. Okay. And wire bonds are typically on the periphery. Can you see that? These are all on the periphery of the thing. You take it from the side. It is very difficult to take wire from the central of the die. But in flip chip you can have it anywhere, central, edge, periphery, anything, anywhere you can have this, and you can bond them. So there is no problem ki you need only the perimeter of the die. In a wire bonding you need the perimeter of the die. Remember, you have a pad here, pad here, pad here, you just take it like that. If you have everywhere, then taking wires out everywhere is a pain. It is a very difficult process, but in flip chip bonding it is not a problem. Okay. So flip chip connections can use the entire area of the die, the whole area of the die you can flip chip bond. You do not need to limit yourself to the periphery. Okay. So this is fantastic, but it is a very expensive tool, and of course characterization and all this, you know, big facilities, they will have a flip chip bonder to enable flip chip bonding. Okay. And the last thing is grounding basically, okay, that we are talking about here. People typically tend to ignore the ground, but this is a very critical component. It is very important. As much as you pay importance to the signal pads, you have to pay importance to the ground pad. Just a simple example will show you that. Suppose I have this transistor whose gate is connected to the drain of this transistor, and I am using a common source for both this transistor, a common ground. Can you see that? Now what will happen is that I have a circuit like that. The drain of this is connected to the gate of this, and the source is here. They are all connected to the ground. Okay. What is the problem here? The problem is it will create instability. There is a ground feedback that is coming in. The signal here can couple and come here. Okay. This ground feedback is going to kill you, your device. It will create instability, oscillation. Okay. Especially for this kind of a cascaded stages, or when you have connected devices in a network sort of a thing, your common ground can really create instabilities. Okay. So then the solution is to create separate ground, which means you bifurcate this thing. One device is this, correct? You have its own ground, and then you are feeding it to the gate of the other thing, okay, and then this will have its own ground. You separate the grounds separately. So you can use a ground connector from the individual device to the ground pad like this, and then this ground can be connected to a global ground later on in a subsequent stage. Okay. But in general, the grounding is a very important issue. One has to keep in mind about this, because the same ground can lead to instability or oscillation. Okay. So with that, we will conclude the lecture here today. These are some of the books and that I had referred for this discussion on passives, on Smith chart, on microwave networks, and you can see that there is a link here in YouTube from which I took reference for discussing on the Smith chart, among other things. I have also taken help from these books for some of the Smith chart thing. So thank you for your time, and I will see in the next lecture, where it will be next week, where we are going to start the last module of this course, which will be on wafer measurement, de-embedding, and little bit or very basics of power amplifier. Okay. So thank you for your time.